All right, so proof of path independence. Okay, so what we are assuming is that here's your curve C, and the beginning point is A, and your final point is B. And I want to prove this. Now let's see how it's proved. First, what is gradient of f? This is just write all the partial derivatives and write it as a vector, right? That's what gradient is. I'm going to prove this only for two-dimensional ones, but three-dimensional is nothing different. You just put round f, round z. It's exactly the same thing. Okay. All right. Now let's compute. Divide by dt, multiply by dt. So you have round f, round x, round f, round y, dotted with dr dt. No. dr dt times dt, and t goes from A to B. Okay. When t is A, you're at point A. When t is B, you're at point B. Okay? So that's what we have to compute. Right? Now let's actually write down what dr dt is. What's r? R is made up of the function for the x coordinate and the function for the y coordinate. Is that right? So we can furthermore rewrite this as round f, round x, comma round f, round y, dotted with dx dt, dy dt, dt. And then we compute the dot product, which is multiply the x components together, multiply the y components together, and you add them up. That's how you compute the dot product. Now, take a moment to look at this one. We've seen this somewhere. Where? When did we see this? A few weeks ago, right? Okay, hint. Something rule.
The chain rule.
Chain rule, thank you. It's the chain rule, right? If your function is a function of x and y, and they're both functions of t,
You look funny too.
this is the rule for what?
Yes, that's
Yeah, but what does this compute? You're not supposed to forget things in math. You have to remember every single thing. Okay? That was the chain rule. So now we can rewrite this as okay, then think about the following. I'm differentiating by t and then integrating by t. What do I get? You get the function back, right? Right? You get your function back, right? And then you have to evaluate at t equal to a and t equal to b, right? But when t is a, which point are you at? Point A, right? When t is b, where are you at? Point B. Therefore, it will be same as evaluating the function f. By the way, f is a function of x and y, so you have to really plug in t equal to a, x and y to get the value of x and y. But when you plug in a, x comma y gives you the location for a. And same thing, t equal to b gives you the location for this b. So that amounts to calculating f of b, f of a. Okay. So that's the mathematical proof. Really what I'm trying to say is that if your vector field given is a vector field of some, it's a gradient of some function f, then this above equation holds. Okay? And that's the mathematical proof of it.